Hi, welcome to another video. In this video, we're going to explore stability of critical points a little bit more in depth. We'll deal with some harder problems. We'll talk about how in the world you can have a spout and a funnel in the same problem. So we're going to take a look at 4 examples first, going all the way through. We'll start with critical points. We'll talk about whether they're stable or unstable, how that should look on a graph, and then we'll go ahead and solve the differential equation behind it and try to see that they make the same exact graph. After that, we'll deal with 3 examples where we just take a look at the first derivative test, or kind of the sign analysis test for this differential equation as far as the critical points are concerned, and just go straight for the graph, just to get a real clear picture of what these things are doing. So let's start with the first example. We have a differential equation, dx dt, where x is our dependent variable, t is our independent variable, x squared minus 4x. And what we learned in the last video was that when we're talking about a differential equation, that right there is a first order differential equation, or a first derivative, which means that that's a first derivative. So if we ever want to find critical points, just like calculus 1, all we've got to do is take this function, which is the first derivative of some higher function, and do the first derivative test on that function itself. So if we're looking for critical points, all we've got to do is say, hey, our function here is x squared minus 4x. And if we set that equal to 0, we're going to find critical points very easily. If that's this same function, and this function is a first derivative, then setting a first derivative equal to 0 gives us critical points. So let's take this and say, hey, if we factor out an x, makes it a lot easier by the zero product property to find our critical points. We get 0 and we get positive 4. So our critical points are 0 and positive 4. Now, there's no way for us to say right off the bat that those are stable or unstable without doing some sort of a sign analysis test or just a first derivative test. The way I showed you in the last video to do that is do something very similar to what we had in like a calculus 1 or even calculus 2 level class, where we take our critical points, we put them in order on some sort of a number line, and we basically say, hey, if that's a first derivative, where this is positive, our function will be increasing. Where this is negative, our function will be decreasing. And where this is 0, our function will be constant or horizontal. So we know that from our first of our calculus 1 days that this function is only going to be 0 at 0 or 4, which means that our function itself, the higher function, the parent function here, is going to have a peak or a kind of an anti-peak or a valley at 0 and 4. That's where our slope will be 0. Now, anywhere else, our function is going to be climbing or falling if this function is continuous. So what we're going to do is say, since this is based on our function f of x, let's plug in something in this range, like -1, 1, and 5, and let's see what happens. And this is going to tell us whether our critical points of 0 and 4 are stable. Remember what stable means? Stable means that on both sides of that critical point, our function is tending to go towards it. Unstable means away from it. Semi-stable is from one side we're going towards it, for another side we're leaving it. And that's what semi-stable is. We're going to see that in the next few examples. So let's plug in a number like, I don't know, -1. Now remember that this is a slope. All we're caring about is whether it's positive or negative. We don't care about the actual value. We care whether our function is increasing or decreasing on this interval. Since this represents a slope, this is a first derivative. This represents a slope. It'll tell us if the slope is positive, whether our function's increasing, or negative, whether our function's decreasing. So when we plug in -1, we say, all right, -1 in our function. -1 squared is 1. 4 times -1 is -4. 1 plus 4 is 5. Now, I don't care about the 5, but I care about the fact that it's positive. What that means is that our slope is positive. So remember our parent function. This would be the slope function of our parent function. Our slope would be positive for this interval. Our function, therefore, so if I were to solve this, I'm going to get the parent function, the higher function, our potential function. Our function here would be increasing. So since our slope is positive, our function is increasing. And if you wanted to show a little bit more work, you'd say, hey, for x values less than 0, this means that our function is positive. And you can show that. Does it really matter? I'm not sure. It kind of depends on if you're taking a class, what your instructor wants. For me personally, I'd say this is good enough. This says what you're plugging in. This says that for this interval, our slope is positive and our function is increasing. Now, how about for 1? If we plug in something like 1, if I plug in 1 to my derivative here, to my first derivative, to the function that represents the first derivative or our slope, well, 1 minus 4 is negative. That means that for this interval between 0 and 4, since 0 and 4 are the only two places where our slope can change sign, every value in here is going to have the same output. It's either going to be positive or negative. So I don't have to go plug in a lot of different numbers. We've already found where we have our zeros, our critical points, 0 and 4. Every number between here, stemming from our Calculus 1 days, is going to have the same sign. And so when I plug in 1 and say, hey, that's negative, that means if my slope for my potential function is negative in this interval, then all of that family of functions that I'm about to find are decreasing. Now, I said something there that you need to kind of remember a little bit. Since this is a first derivative, since this is a differential equation, it's a first derivative for a whole family of curves. And so what we're doing is pretty profound. What we're saying is that for all of those functions for which this is the slope, all of them are going to be increasing from negative infinity to 0. All of them are going to be decreasing from 0 to 4. And then if we plug in 5, you go, okay, 5 squared minus, that's 25 minus 20. That's another positive, it's positive 5. All of them are going to be increasing from 4 to infinity. And that's fantastic. We don't know exactly what our function is because it's going to, solving this differential equation is going to give us a general solution, a family of curves. But depending on what our initial condition is, we'd be able to find a particular solution. What this is saying is that all of our general solutions, or our general solution, all of our curves here, are going to be increasing on the interval of negative infinity to 0, decreasing on the interval of 0 to 4, and increasing on the interval from 4 to infinity. That's pretty cool. That means that this goes increasing forever. Now, so if that represents the entire general solution here, we can say that for every single particular solution in that general solution, so solving our differential equation, all of them are going to have a stable critical point at x equals 0. Notice how our function, no matter what it's going to be, has a positive slope and a negative slope. They're going to increase and decrease around that x equals 0. That's called a stable critical point. But around 4, we get something different. We say that around 4, if we're below that, our function is decreasing, our slope is negative. Our function is increasing above that, our slope is positive. And we're tending to go away from that. That's called unstable. Now, how is it going to look? I'm going to come over here and I'm going to show you. And then we're going to go ahead and solve this differential equation. We're going to see that it gives us the same exact graph. So if I have these two critical points, x equals 0 and x equals 4, I want to make sure I put them in order. Here's what's going to happen. With our stable critical points, our general solution is going to, no matter where we start, our general solution is going to tend towards it. For our unstable critical points, no matter where we start, our general solution is going to go away from it. And so when we have two or more critical points, these things sort of interplay off one another. So if I start below x equals 0, what this says is that if I start, now let's put all this together, okay? This is a first derivative. This says that this is the slope for every potential function that has this as a slope. That means that I'm going to have some arbitrary constants, aren't I? And the arbitrary constant is going to give us sort of this initial value dependent function. If my initial value starts below x equals 0, I'm going to be increasing. If I start below x equals 0, this is going to give us a picture of our general solution based on this. So if I start below x equals 0, I'm going to be increasing. My function is going to be increasing. It's going to go like a funnel. It's going to funnel into this from below. So I'm going to funnel into x equals 0. It says I have to increase. Where am I going to increase? Until I get to x equals 0. Now what about above that? If I start above x equals 0 or between 0 and 4, I'm going to be decreasing. Now that says both of this. It says I'm going to go away from x equals 4. I'm going to go towards x equals 0. So no matter where I start between here, I'm going to be moving away from x equals 4, but towards x equals 0. That's what this says. If this is our slope, it says you're decreasing in this interval. No matter what your initial value is, your function will be decreasing. Kind of depends on where I start, but where I start, no matter where I start, I'm going to be decreasing somehow. Now, above 4, I will be having a positive slope for every single particular solution, depending on what our initial value is. I'm going to be increasing. So where I start doesn't really matter as far as what I'm doing. It'll give us a particular type of curve, but this says no matter where you start up here, you're going to have a positive slope. You're going to be increasing. Now, we can get a very clear picture of our general solution with just this work. That's why I said earlier in the last 3 examples, I'm just going to be doing this. I'm just going to show you these curves. I'm going to practice doing some differential equations so you see some more advanced techniques. But in general, this is really all that we kind of need to get a clear picture of it. So what we're doing, taking a first derivative, doing a first derivative test, allowing that to give us a general solution or a picture of our general solution. So let's do it. It says below 0, I'm stable. So that means I should get a funnel here. So if I start below here, we should get a funnel. Notice how I have several curves. You go, why do you have several curves? Well, this is a picture of our general solution. So without a particular initial value, we can't get a particular solution. All we can say is that all of these curves are going to be increasing depending on a value less than 0. If our initial value starts less than 0, you are going to be increasing. Now, what if our initial value starts between 0 and 4? You're going to be decreasing. So we're going to have several types of curves here. We're going to get some that look like this. And as we get closer to our 4, we're going to get curves that look like going away and coming to that 0. This is called a funnel. When we get towards a value from both sides, that critical point, this is funneling to that x equals 0. We're leaving this 4, that's a spout, we're going to be leaving this. We're spouting away from the 4, funneling into the 0. So when I said that we have a general solution here, this could be, you could be any of these curves down here, any of these curves down here, or any of the ones we're about to get up here, depending on what your initial value is. So if our initial value starts less than 0, we're going to climb to it. If our initial value starts between 0 and 4, we're going to go away from the 4 and towards the 0. If our initial value starts above 4, we're going to be leaving that 4. And that's a fairly clear picture. Now, this is not a computer program, unfortunately. Not a computer. That's probably fortunate. But it'll give you, depending on how well I can draw these things, a clear picture of what our general solution is. Again, there's not just one curve here, because what our particular solution depends on is a starting point, an initial value. If our initial value is somewhere down here, we're going to climb to 0. Somewhere between here, we're going to fall to 0. Somewhere above here, we're going to go away from that 4. This is what stability and instability looks like for critical points. We go to it in what's called a funnel, or away from it in what's called a spout. I hope that makes sense to you. Now, what we're going to do is we're going to go through and we're going to solve this differential equation. It looks like we're going to have some partial fractions here. So separable differential equation, partial fractions, we'll go through it fairly quickly because I've done it so many times with you. But what I really want to get at is 2 main ideas. Number 1 main idea is this function is a slope function for some sort of potential function or some sort of parent function or something we haven't found yet, some function we haven't found. So when I do a first derivative test, I don't take another derivative. That would be a second derivative test. So I'm not really concerned about concavity. It would tell you this a little bit better, but I'm not concerned about that. I'm concerned that if this is a first derivative, it will directly give me critical points set equal to 0. That's important. Being able to do a first derivative test is pretty big. Second thing, when I take this and I make a graph from it, what I'm taking is a picture of our derivatives, our first derivatives, and letting that tell me what our general solution is doing, whether we're increasing or decreasing on an interval. That's going to give us a fairly clear picture of a general solution. It means you're going to get lots of curves because we're saying that we don't have a particular solution, or sorry, a particular initial value, so we can't get a particular solution. You'd have to have an initial starting spot to say whether you're down here and climbing, between here and falling, up here and climbing. You'd have to know that. Otherwise, we get a picture of a general solution that's lots of curves, it's a family of curves. So just be aware of what we're doing when we're doing this, okay? First derivative is slope, and when we start getting a graph of those family of curves, we're getting a general solution. We're going to see that in our solving of differential equations. So let's do it. So we know that this is factorable. We've already done that. And if we separate our variables here, and we take an integral of both sides. Right-hand side, very easy. Left-hand side, we're going to have partial fractions. So 1 over x minus 4. Remember that linear factors give us fractions. Linear gives us a constant numerator. We're getting a common denominator here, so we're going to multiply x minus 4 and x. And since we have an equation here with the same denominators, that's why we find a common denominator, our numerators would also have to be equal. And so when we find a common denominator and it alters our numerators, we just have to set our numerators equal. And we do some fancy stuff like, hey, what if x were 0? If x were 0, then this would be 0, this would be negative 4, and 1 would have to equal a times negative 4, giving us a equals negative 1/4. Or if x is 4, then this would be 0, but this would be b times 4. So 1 would have to equal b times 4, and b would give us 1/4. And now we can rewrite this as something that's a little easier to take an integral of. We'd say, hey, this whole fraction is a over x, b over x minus 4. If a is negative 1/4, that's negative 1 over 4x plus 1 over 4 times x minus 4 dx. And you see me do this a few different ways. I've always factored out this denominator here, this 1/4. Sometimes I'll factor the negative, sometimes I won't. And if you're wondering why I do that, I've explained it a couple times, but I like my single term denominator to be negative. That way when I make my ln, I combine these two natural logarithms into one, I have a single term on the denominator. That's kind of nice. Next thing what I'll do is once I factor that out, this 1/4, you've seen me go ahead and integrate right now. You've also seen me multiply by 4. That's really up to you. I'm going to multiply by 4 right now because I just want to get rid of that. Do you have to? Nope, it doesn't really matter. Because that arbitrary constant, whether you multiply by 4 now and call whatever you get upon integration c, or integrate now and multiply c times 4, you still get an arbitrary constant. It doesn't really matter. But it's a little cleaner to multiply by 4 right now. Clear this out. So I'm going to multiply by 4 on both sides. I'm also going to integrate. So when we get the integral negative 1 over x plus 1 over x minus 4, equals 4 times the integral of dt. So we're just multiplying by 4. On the left-hand side, yeah, we're going to get a negative ln absolute value of x. We'll get another ln absolute value of x minus 4. On the right-hand side, we simply get 4t plus c sub 1. You've seen it many times. We're going to call that c sub 1 because we're about to combine these natural logarithms. use an exponent on both sides, and that right there is going to change. We're going to get plus or minus e to the c sub 1. We're going to wrap all that up as c. If you didn't multiply by 4, and I've done it both ways, if you didn't multiply by 4, right here you'd have a 1/4, and you'd multiply by 4 now, giving us a 4t plus 4c sub 1. That 4c sub 1 doesn't matter. It's still arbitrary constant. So let's combine our logarithms. Exponent on both sides. When we do that, we're going to wrap up a plus and minus e to the c sub 1 times e to the 4t. Oops. And this whole thing is going to become our c, our arbitrary constant. So x minus 4 over x equals c e to the 4t. Now, let's pause for a moment. Let's think about what we're doing. You've heard me mention that this is a first derivative. It tells us slope of a general solution. Okay, that tells us what our general solution is doing as far as increasing or decreasing, and we learn that it depends on the initial value. That's why we get a whole bunch of potential curves, potential functions here that are either increasing, decreasing, or increasing depending on what our initial condition is. Well, we better find out an initial condition, or at least have some way to show that in our work. So with that arbitrary constant, let's make it represent our initial conditions. What's our initial condition? We don't have one here. Well, when we see that, we go, our initial condition would be some value at time 0. So whatever our x value is at time 0, let's call it x sub 0. Plug that in, and it will allow you to solve for your arbitrary constant right now. That arbitrary constant will be this value that depends on an initial condition. It will tell us where we start and what our curve looks like depending on that. And so when we do this, we go, okay, let's allow x sub 0 to be x sub 0. So the x value at time 0, right there, that's going to be 0, is going to be x sub 0. Let's plug that in. So x sub 0 minus 4 over x sub 0 equals c times e to the 4 times 0. So when t is 0, our x value is x sub 0. Notice that what this is going to allow us to do is create this general solution where all we need to know is what our value starts at. Think of it as population, what our population starts at. And then we can plug it in, and it will tell us where we are, what our particular solution is. So our c value, since this is 1, equals x sub 0 minus 4 over x sub 0. Now this is super nasty. I don't really want to go plugging this in because, can you see it? I got a fraction of the deal with all that junk. So here's what I'm going to do. What I'm going to do is I'm going to keep this as a c as long as I can. And at the very end, well, whenever I can't keep it as a c reasonably anymore, I'm going to now plug this in. So I'm thinking of this in my head, thinking, C is this? I'm just going to not plug it in right now because otherwise I have a lot of complex fractions. I have a lot of common denominators I have to find. I might have to do that later, but for now, just for ease of working with it, I'm going to keep this as a C, and I'm going to solve for x as much as I can. So what that means for us is I'm going to multiply both sides by x. I'm going to get our x's on one side, our constant on the other. I'm going to factor an x and then divide. So I'm going to multiply by x right now. I'm going to group my x's on one side, non-x terms on the other. We're going to factor an x. We're going to divide. Remember that this x is a function of t. It is a function. At this point, we can't go any further without using this. But do you see what happened? Now, maybe you want to try it. If you want to, you can plug this in right here and go through it, but your x sub zeros and your x's, I see a lot of students get those confused. If you drop that initial value, this x sub zero starts looking a lot like an x. And then you go, oh, junk. If I mess that up, my problem's pretty much smoked. So this is my preference. My preference is I like to keep it as a C. Of course, everything I talked about differential equations stays where it is. Okay, don't relearn anything here. What I'm showing you is as soon as it's possible, you do solve for your arbitrary constant. We've done that. We're just not plugging it in yet. Okay, we're being smart about it, saying this is what it is. Let's solve for x. Boom, and then we can plug in our initial value. So once we've done that, we go, okay, this right here, this is x sub 0 minus 4 over x sub 0. And Leonard, that doesn't that doesn't look so great. And not only that, it's not what's in the back of my book or wherever you got this problem or whatever you're working on. You're right, but you see what it does. It says instead of working on with a complex fraction or some sort of fraction all the way through this problem and having to distribute with it and factor with it, it allows you to say, well, now that I have a simple complex fraction at the very end, I can do things like, hey, how do you simplify complex fractions? Well, you multiply by the LCD, or least common denominator, lowest common denominator, which is just x sub 0. And if you remember that you're going to distribute that, then our function becomes 4 x sub 0 distribute x sub 0 minus, these are going to cancel when I distribute. Now I absolutely have to put a parentheses around this because it is multiplied by e to the 4t. But that's it. That's a lot nicer than working with this fraction all the way through. So one time, then we'll talk about what that is. One time all the way through, you start with differential equation, first order differential equation, and you are starting with the slope of some sort of higher function, some parent function, potential function. If you're starting with the slope, do a first derivative test. It tells you what your function is doing. It tells you that for certain intervals, you're positive slope, negative slope, positive slope, increasing, decreasing, and increasing. That'll actually give you a picture of what your general solution will do. Lots of different curves here because we're talking general. It requires these things have a general solution, right? Arbitrary constant gives you a general solution. This is giving you a general solution. You need a particular initial value to get a particular solution. That's why we have this arbitrary constant solved for an initial condition or initial value problem. When we use that, this says, depending on what your initial population is, or initial starting amount is, it's going to give you one of these curves. Not all of them, one of them. This is general. This is everything that could possibly happen. This is every slope you could possibly have. This is every particular solution you could possibly have. It's called a general solution. Finding one of them requires a single value. So if our values, let's take a look just to make sure we're really clear. If our value is less than 0, that would be negative. If it's like -1 or something, this would be a negative. Let's see, this would be -1. This would be a negative. Oh, but wait, this is positive, isn't it? So something positive. This right here is something less than 0. Negative. Positive. This would be something even more less, so -5. But adding that, you're going to get a negative over negative. That's a positive. You are going to get something that is, oh, I'm sorry, so the slope would be positive. The function itself will be negative, but getting closer and closer and closer to 0. If we start between 0 and 4, so something like 1, that would be positive, that would be positive, that would be negative. Depending on what that value is, you're going to get something between 0 and 4. Our slope will be negative, however. So we're going to be consistently dropping towards 0 as we continue. It would be a decreasing function. And lastly, if we start above 4, we're going to get something that's increasing. So this right here is modeled by this graph right here that we've drawn. It depends on what your initial condition is in order to get a particular solution. I hope that makes sense. We're going to do a few more. I'm not going to go as in-depth on my explanation as I've just done with you. We're going to basically get picture, practice doing our differential equations, and we'll move on after that. So hang on, I'll see you in an example in just a second. All right, here we go. Let's take a look at this first order differential equation, which means we're dealing with a slope. This is a slope of some sort, a slope function of some sort of a potential function that we've got. Now, what we're going to do, we're going to say if this is our function, then this represents the first derivative, and therefore we can do a first derivative test to find out the critical points. Let's try it. So our function looks like we might be able to factor it. There's a good clue there for us. It's a difference of squares, if you do it right. And set it equal to 0 is exactly how we find critical points. So our critical points are 2 and negative 2 by the zero product property. Let's do a first derivative test. Now we always want to make sure these are in order because it does represent a number line for us. But we're going to plug in values that say, hey, if this is a slope, then everything in this interval is going to have, every potential function in this interval is going to have the same slope, positive or negative. Same thing here, same thing here. These are the only places, x equals negative 2 and x equals 2, those critical points where our slope can change signs. That's it. And so what we're going to work on is, hey, let's plug in something like negative 3, see what the slope is doing. If we plug in negative 3 to our function here, let's see, that's 9 minus 4, that's positive. I don't really care that it's what the actual value is, but what I do care about is that this is positive. That's increasing. How about 0? 0 minus 4 is negative. And how about 3? 3 squared minus 4 is positive. So this tells us that our function itself, by plugging in just a single value here, they're all going to have the same value of sign of slope. So positive, negative, positive says we're going to be increasing, decreasing, increasing, no matter where we start. If our initial value is in this interval, our parent potential higher whatever function is going to be increasing, it's going to be decreasing in this interval, it's going to be increasing here. Right now you should tell me which of these are stable and which of these are unstable. We should know that this is stable, this is unstable. You should have a picture in your head of what is going on right now. You should understand that right here, this is going to be a funnel. Things are going towards, this function is going towards negative 2. This is a spout. Things are going away from positive 2. So when we take a look at it, this is funneling towards and spouting away. We have this funnel idea and a spout idea again. This is what our function should look like. Depending on where we start, we're going to get one of these curves. Something increasing to negative 2 or decreasing to negative 2. Something increasing away from 2, away from 2. So we have this funnel and spout idea. Let's solve that differential equation. Let's see if we can get a general solution that is modeled by this picture of our general solution. This is giving us this spout and funnel. Hey, let's solve it. It's kind of fun to solve anyway. So we already know that this is factorable. Let's go ahead and let's keep this factored. Especially when I know that I'm getting some functions that are going to be solved by partial fractions. I leave it factored, so a little bit easier that way. Let's group these variables, so separate our variables here. If we integrate both sides, we immediately see we are going to have some partial fractions. So let's take a look at that right over here and say, hey, you know what? If I take a look at my partial fractions and let the number of factors equal the number of fractions that I get, understand that linear denominators give us constant numerators. Say that if I find a common denominator here, we're going to say that our numerators would have to be equal a times x plus 2 plus b times x minus 2. Plug in 2 and negative 2, and it's going to allow you to solve for a and b very nicely. So if x equals 2, that would be 0, that would be 4, a would have to be 1/4. Likewise, if x is negative 2, that would be 0, that would be negative 2, b would be negative 1/4. I know I've done that very quickly, but that's why I gave you a whole video on how to deal with partial fractions, because this should be, at this point, very, very understandable. The only thing I'm really trying to teach you is that that's a first derivative. Let the slope tell you what your general solution is doing as far as increasing and decreasing. Learn what stable and unstable mean. Be able to get a picture of your general solution without even having to do any work. That's pretty cool. So this will give you a population model, really, for where I start matters. If I'm below or between or above, it's going to show you what your particular solution is without even doing any work. Hard work. So now that we're able to say that our a is 1/4 and our b is negative 1/4, we can alter our integral. So we've got this integral of negative 1/4. Let's see, a was with the x minus 2. So a is 1/4. That would be a positive, and then x minus 2. Minus 1/4 x plus 2. Now, I don't really care about factoring out that negative. Because I'm going to have two terms no matter what, I'm just going to factor out the 1/4. You see me do this in the last example. We'll multiply by 4 and then we'll integrate. So if we factor the 1/4, and we multiply both sides, makes it just a little bit cleaner. And we integrate, we're going to have a natural logarithm, x minus 2, minus on that natural logarithm, absolute value x plus 2, equals 4t plus c sub 1. We're going to do the same exact thing as last time. We're going to group this as a single natural logarithm. We know that subtraction gives us a quotient, where everything subtracted or negative goes on the denominator, everything positive or plus goes on the numerator. And we get this 4t plus c sub 1, same exact thing. I'm going to do all of it at once right now. We're going to take an exponent on both sides. We'll wrap up a plus or minus e to the c sub 1 as an arbitrary constant. So absolute value, e, and c sub 1 are all going to be c, but we'll still have an e to the 4t. On the left-hand side, we simply get x minus 2 and x plus 2. So we're taking both of these as an exponent on that natural number. We're saying that this would separate into two different factors, e to the c sub 1 and e to the 4t. But e to the c sub 1 is a constant, and absolute value, you can wrap that up as a plus and minus. So plus and minus e to the c sub 1 is a constant. Now what do I do now? Do I want to solve for x now, or do I want to find my arbitrary constant now? Arbitrary constant as soon as you can. It's not great here. This is horrible. But here is really nice. So if I plug in x of 0 gives me some initial condition, some initial value problem. Well, then when t is 0, our x value is just our initial condition. That's going to let us solve for c. But I'm not going to plug it in here yet. What I'm going to do is I'm going to save this to the end and see what I can do as far as solving for x before I have to plug that in. So now, let's see. That would be x sub 0 minus 2 over x sub 0 plus 2 equals c times e to the 4 times 0. This whole thing is 1, and this gives us our c. So our c, what I'm going to hang on to in my head, c is x sub 0 minus 2 over x sub 0 plus 2. Now, I actually haven't done it this way on my notes. We'll see if it works. Let's see if I can just solve for x here with this, and then later plug that in. Because if I tried it the first time doing it with this, and it's crazy. There's a lot of little nuanced math in there with common denominators that can really get you kind of all jacked up. And so we're going to solve this for x as much as it's possible with that arbitrary constant that's not so arbitrary. We're just going to treat it that way until the very end. So let's try this. So from here, I would have to, let's see, I'd have to multiply both sides by x plus 2. I'd have to distribute. We're going to group our x terms on one side, non-x's on the other, factor and divide. So it's going to look kind of nasty at first, even though we don't have that. With this thing, it's incredibly nasty. So let's first multiply both sides by x plus 2. That's got to be in parentheses, which means that I have to distribute that. I'm going to group my x terms on one side. My non-x terms on the other. We're going to factor. You can factor here too if you really want to. I don't think it's very necessary. And we're going to divide. So our function of x in terms of t, of our independent variable t, gives us that. We go, okay, all right, so now what? Now what do you do? Right here's where I would plug this in and do the same technique I just showed you. So you're going to get a complex fraction right now, and we're just going to simply multiply both the numerator and denominator by whatever LCD is of that complex fraction. So from right here, you go, all right, let's make sure I've done everything right. I've multiplied by x plus 2, got it. I have distributed this, looks pretty good. I've got my x terms by subtracting, my non-x terms by adding on different sides. I factored, I messed the sign up. Looks the same here. Okay, I've divided, and now we're ready to go ahead and plug in that arbitrary constant that we've solved for. And this right here contains our initial value. So depending on our initial value, it's going to give us a different function. That's why there's so many curves over here. Depending on our initial value, it's going to give us a different function. So 2 plus, let's see, 2. Going to be more room. So that's C, that is this thing. And now we're going to take that and say, instead of the C, since I've worked this all the way down to solve for x, this is x sub 0 minus 2 over x sub 0 plus 2, and likewise down here. But now instead of having to have worked with that and distributed with that, I'm just going to have to multiply both the numerator and denominator by x sub 0 plus 2. Yes, it will distribute. It's still going to be a little bit nasty, but it's a little bit nicer to work with than having it the whole way through that. So x sub 0 plus 2 over x sub 0 plus 2. When we distribute, what's going to happen? I need to distribute this whole expression to the 2, to the 1. It's going to cancel here. So when I distribute this times this, our x sub t is going to give us 2x sub 0 plus 4 because you are distributing this. This is going to get multiplied by the 2. That means that you're distributing 2 onto x sub 0 and 2 times 2. When we distribute to this whole entire term here, our factors x sub 0 plus 2 and x sub 0 plus 2, they're going to cancel. So we do get this, but then we get a plus 2 x sub 0 minus 2 e to the 4t over, well, what happens here? We would distribute x sub 0 plus 2 times 1. That's going to give us an x sub 0 plus 2. 1 times x sub 0 is x sub 0. 1 times 2 is 2. Minus x sub 0 plus 2 e to the 4t. That is about as good as we can get. If you want to leave this factored as 2 times x sub 0 plus 2, it would look like this. That's fine too. It doesn't really matter. It might be a little nicer since you can see it here, but honestly, it's really up to you. So what this is your general solution. Notice how this solution depends on where you start. So if I start with a value less than -2, I'm going to get an increasing graph. If I start with a value between -2 and 2, I'm going to get a decreasing graph. If I start with a value above 2, I'm going to get an increasing graph. What if I start with a value at 2? At -2? Those are called equilibrium solutions. Nothing would change. So anyhow, I hope this is making sense. I hope you're really starting to see how this picture gives us this, and we have to do a whole lot of work to find the general solution, which our first derivative test models fairly nicely for us anyhow. So hang on for a couple more examples. We'll go quickly through them like we've been doing, and then we'll start just doing the pictures. Okay, let's go on a few others. Now, I've shown you a couple times that we can have funnels and spouts in the same problem, but what I haven't shown you is what a semi-stable critical point looks like and what the graph would look like. So we're going to do that with this. We'll talk about a completely unstable critical point in the next example, and then we'll go ahead and deal with a combination of some of them. So let's take a look at the derivative of x with respect to time is x minus 2 squared. So a first order differential equation represents our slope. Let's find our critical points. Now, when our function is set equal to 0, we really just get one critical point. X equals 2 is the only critical point we have. So when we have these repeated factors, zero product property says just take your factor itself, set it equal to 0. It has a multiplicity. What multiplicity means is the degree of the factor that's giving you that 0. So that multiplicity is even. If you remember what multiplicity actually does, it means that on both sides of that critical point, you're going to get this symmetry. So they will have the same value, either both increasing or both decreasing, which means if we take this critical point and put it on our number line, doesn't matter what I plug in, it's going to have the same sign. It's going to actually have the same value, no matter as far as our sign is concerned, about what we're plugging in. So if this is our first derivative, represents a slope, if I plug in something like 3 or something like 1, I'm going to square both of them. I'm going to get a positive. Our slope here is positive, saying that our general solution is going to contain functions that are all increasing. So whether I start below 2 or above 2, I'm increasing. Notice what's happening. If I start below 2, my function is going to increase until increase until I get to 2. If I start above 2, it's going to increase past that. This is called semi-stable. In one interval, I'm increasing to my critical point, but in another interval, I'm increasing away from it. So we're not funneling to, we're not spouting away. This is semi-stable. It's sort of like a funnel on one side and a spout on the other. Now, what that's going to look like for us is that if I have one critical point, if I start with an initial value below 2, this says that every single one of my particular solutions or my general solution is going to be increasing. So we're going to get this increasing, all of these are going to be increasing functions if I start below 2. If I start above 2, I'm going to be increasing. So I'm going to get increasing functions if I start above 2. Notice how from below it looks like a funnel, from above it looks like a spout. That's what semi-stable would look like. I'm going to be increasing to a point or exploding if I have this initial value above that. Now, what would that look like for population? What that means here is that we would either get a leveling off, this limiting population, or I would get this explosion, this doomsday scenario, depending on where I start. So that x equals 2, that equilibrium solution is real important. Start below that, I'm going to reach it. Start above that, I'm going to explode in population. Now let's see what our solving of our differential equation actually looks like. We don't have any partial fractions. That's nice. We actually have something fairly simple. If I treat this like the separable differential equation it is and get my 1 over x minus 2 squared dx on one side and our dt on the other, and we integrate, you can look at this as a simple u sub if you need to. And say, hey, u would be x minus 2, but the derivative of x minus 2 is just 1. So if you can just cover that up and say the derivative is not going to give us any sort of a constant that we need to divide by, then we would say, let's see, u to the negative 2, I add 1, that'd be u to the negative 1 over negative 1, and I put my u back in there to x minus 2. So this would all become negative 1 over x minus 2. U to the negative 1 over negative 1. So that'd be a negative sign, and then we get x minus 2 to the negative 1 power, or 1 over x minus 2. On the right-hand side, we just get t plus c. Now, it's great juxtaposition of what we're about to do. You see in the previous few examples, like for a lot, when we had partial fractions and lots of ln's, we combined those, we took the exponential on both sides, and then we solved for that arbitrary constant. Here, we don't have to do that. You should be solving for your arbitrary constant now. There's no e, there's no c sub 1. It's fine, do it right now. So when I say that our initial value happens at time 0 and would give us an initial value of x sub 0, our x would be x sub 0 when our t is 0. And that lets us solve for our arbitrary constant right now. It says that our arbitrary constant is based on our initial condition, where we take 1, negative 1, over initial value minus 2. We're going to hang on to that for a second. We're going to solve this for x. So remember, we're putting this in our heads and saying this is what c is, but I would solve for x first. So how in the world would I solve for x? Now, I might change signs, might do that. You don't have to. I would do that. If I change signs, so starting from here, multiply both sides by negative 1. Then 1 over x minus 2 would give us negative t minus c. Now, something you can't do. Because this c is already defined, don't go changing that sign right now. That's going to mess everything up. So this c is this thing right here. If you're going to start changing this and saying, oh, well, let's just make that plus c, you would have to define this as c sub 1. You'd have to have some sort of a c equals c sub 1, c equals negative c sub 1. And then you go ahead and do that, but you'd have to backwards map it. So my encouragement to you is don't do that. Don't change that sign, because it gets very confusing, and sometimes we'll mess some signs up if we do that. So I'm going to just leave this as minus c, understanding that I've already solved for that. This is a thing right now, okay? If you'd have had that in there, wouldn't you be changing that sign? Yeah, of course you would. So don't be taking this and wrapping that up as a general arbitrary constant right now, because you've already solved for it. You're just holding on to it until the very end. I hope you get that. Now, because I have 1 over x minus 2 equals negative t minus c, I can make this basically reciprocate both sides. I can say that x minus 2, therefore, would equal 1 over negative t minus c. If we add 2, do I want to do that right now? We could. If I add 2, we get 2 plus 1 over negative t minus c. Here's a good time to do one of two things. Either you can factor out a negative and change the sign to a minus. I'm not going to do that. Or you can plug in c right now. I am going to do that. Why I'm not factoring the negative is because that's negative. And what you do is subtract that negative. It's going to change to a plus anyhow, and that's really what I want. So I'm going to do it that way. So here's our general solution. In terms of t, we have 2 plus 1 over negative t minus c, but I know what c is. C is that negative 1 over x sub 0 minus 2. So let's simplify this a bit. Now, what in the world do we do now? Because that's a complex fraction. Well, we know that we're going to multiply by the LCD, or the only denominator that's here. What we don't do, we don't multiply this here and then accidentally distribute it to here. That's not something we need to do. That too is fine. Just leave it. Now, in a moment, once we take care of this, we are going to find a common denominator. We're going to make one fraction out of it. But you don't distribute this x sub 0 minus 2, you don't distribute it to it. So when I multiply by x sub 0 minus 2 over x sub 0 minus 2, it's just to this fraction. So this thing gets multiplied times 1. This thing, yes, it gets distributed here. So x sub t is 2. Don't distribute it here. Plus x sub 0 minus 2 over, when we distribute this, we're going to get negative t x sub 0 minus 2 plus 1. That's going to cancel that denominator. I might reverse these just a bit. Now, you can leave it just like that. My preference is to. If you have to, if it doesn't look quite right to you, you'd have to find a common denominator with this 2. So you'd be multiplying times this denominator over itself, and then you could combine this fraction. I'm not going to do that. The reason why I'm not going to do that is this shows really clearly where that number's coming from. This says, hey, you're starting with a shift up. Remember that constantly shift up of 2, and then depending on what your initial value is, you're going to get a increasing curve with 2 different concavities. Yeah, probably. So we have this increase, but only until we get to that 2. And I like that 2 there because it shows us that vertical shift. So anyhow, I hope that's making sense. This is our general solution. It is based on an initial value, and so is this. So we'll deal with one more all the way through. We'll change that exponent and see what happens, and then we'll talk just about some pictures. All right. Ready for our last one all the way through. Now, we've changed just two small things. We're going to give a completely different look at a solving of a differential equation and a completely different look of what our general solution is. So that's a first derivative. That's a differential equation, first order differential equation. It represents a slope of some sort of potential function. That means that if that's a slope function, we can do a first derivative test to solve for critical points. And again, we just get one critical point. Our multiplicity is odd. What's that mean? That means that on both sides of this critical point, we're going to get opposites. So odd multiplicity says that you are reflected about the origin, and even means you're reflected about like a y-axis sort of idea. And so here we're going to go, all right, if our critical point is 1, we do this on a first derivative test. or a sign analysis, or whatever you want to call it. Now I plug in 0, I'm going to get a negative. If I plug in 2, I'm going to get a positive. Saying that our function is doing two different things. To the left, or on the interval from negative infinity to 1, all of our particular solutions, or a general solution, they're going to be decreasing. Our slope will all be negative there. Greater than 1, we're all going to be increasing, or our slope will be positive, which says that every particular solution, if we start above 1, is going to be, with initial value, is going to be increasing. That right there is a completely unstable critical point. What that means is that for below x equals 1, we're going to be decreasing. And above 1, we're going to get functions that are increasing. Now, they might look different than this, but in general, that's exactly what we're going to get. Do I really want it? No, I don't want to do that. So that right there says that we're going to get a spout. Now, let's go ahead and solve this differential equation, see if we can see that as far as our general solution is here. Again, we have this separable differential equation where we can group our x's on one side dx, our constants dt, and take an integral of both sides. We have this u sub again. Where we can imagine a derivative of x minus 1 is just 1, so it's kind of a trivial u sub. I like to cover that up and say, okay, if that's a u to the negative third power, I would add 1, that's u to the negative 2 over negative 2. So I'm going to get this negative 2 over u, or x minus 1 to the negative 2, or squared, equals t. Oh, I messed up. Sorry. Let's see. I think I have my 2 in the wrong spot. So let me just do my u sub. Integral of u to the negative third power du would give us this u to the negative 2 over negative 2. Yeah, see, I messed my denominator up. That would give us this x minus 1 to the negative 2 over negative 2, or negative 1 over 2 x minus 1 squared. That right there is what we get from our left integral. So negative 1/2 x minus 1 squared equals t plus c. Now I'm going to do a c sub 1 for just one reason. I don't really want to deal with an initial condition or an arbitrary constant that has a 2 in it. And so what we can do here, and because you have a lot of canceling out, what we can do here is multiply both sides by 2 right now. We can even get rid of that negative as long as you don't solve for the arbitrary constant first. This is something that you can redefine as your arbitrary constant of c. You can't do that if you solve for your arbitrary constant first. So there's some nuances in how we do this. You've seen me solve for the arbitrary constant like right away with the initial value problem. You've seen me do some stuff with logarithms. You've seen me wait a little bit. It's really up to you. Look at the problem, study the problem, see what's going to benefit you. Because I'm going to hang on to the c until the very end, I want it to be as simple as possible. So I'm getting rid of my negative. I'm getting rid of that 2. I'm going to say, let's call this thing the arbitrary constant. And now when I solve for it, when I say, hey, my initial value would happen at a time of 0, that's going to say that when t is 0, this thing still goes to 0, even though it's not just t, it's negative 2t, but who cares? It's still going to 0. I'm going to get 1 over x of 0 minus 1 squared, and that's going to be negative 2 times 0 plus c. That says that our c is no longer arbitrary, it's based on an initial value. It's 1 over x sub 0 minus 1 squared. Now we're going to solve for x, but we're going to wait to plug that in. That's going to be like our little secret guy over here, that we're going to solve for x from here, but we're going to wait to plug in c that's right here to the very end. Now, one thing I don't want to do, I don't want to start going back up here and solving for x, because I've redefined that, right? So I've modified this problem to get an arbitrary constant. I've solved for this c. So you have to use this to solve for x. You can't be going back because you're talking about different constants there. You'd be altering this constant. It would no longer be the same. So since I've based my arbitrary constant, finding that initial value from this particular formula, I'm going to use this particular formula to solve for x. What that means is we have something very similar we've done. We're going to reciprocate both sides. So here we have this x minus 1 squared would equal 1 over c minus 2t. So I've switched this around. We reciprocated both sides. Oh, now what? We've got to take a square root. Awesome. We've got to add 1. And you go, well, what happens when you take a square root on both sides? Shouldn't you have a plus and minus? Yeah, you should. When you take a square root on both sides, you should have plus and minus. Positive, negative, square root. That's what these graphs are going to look like. I hope that you're seeing the horizontal, the vertical shift. Here's our 1. Here's a square root function that's positive or negative. It's going to give us a different look here. This is just an approximation of what it looks like. This is the actual graph. And now we're ready to plug in that arbitrary constant that's not arbitrary any longer. So a couple things, let's see. Number 1, I don't need the square root of 1. I can simplify that. I'm not sure I want to yet. I'll tell you why in just a moment. So I'm going to leave that as a square root because we're going to end up getting, based on this c, a 1 over x sub 0 minus 1 squared. Minus 2t. The reason why I'm not simplifying that 1 is because if I did, I'd have to go ahead and make this under a square root anyhow. What I'm going to do is I'm going to multiply both the numerator and the denominator by the LCD of that complex fraction. That's going to multiply by 1, and since I left this in a square root, it's really easy to see that this square root and that square is going to cancel. That's kind of nice. I'm going to leave it just like that. This will distribute, cancel here, but I'm going to have this minus 2t, or 2x sub 0 minus 1 squared times t. So using just a little bit of simplification here. We're going to still have a 1, we'll still have a plus and minus, we'll still have a square root, but inside that square root, we're going to have an x sub 0 minus 1 squared all over distribute, it'll cancel, but it'll give us a 1, not a 0. So 1, cancel, minus 2x sub 0 minus 1 squared, and we still have a t. So let me check my work here. I've multiplied by 1, I got that. This is going to cancel. I've multiplied a distribution on this expression. I've canceled that. I've got a 2x sub 0 minus 1 squared times t. That looks really good. Now we're going to simplify one last thing. And get a 1 plus or minus, we'll have an x sub 0 minus 1 all over a big square root of 1 minus 2 x sub 0 minus 1 squared t. That's about as good as we can get. To go any further, you'd have to get a common denominator, start looking really nasty. We really don't want to do that. But this shows us what's going to really be going on with our our general solution. So what we've done is we use some general curves to represent what's going to happen around our critical points, whether we're spouting or funneling or semi-stable or not. But when we solve this, we get the actual look of our curves. So I hope that's making sense. I'm drawing these just off the top of my head, just kind of giving you a look of it. The curves themselves are going to be different, which is why it's important to solve these all the way down and say, hey, this is what it really, really looks like, okay? It depends on what your initial value is. If it's less than 1, yes, we're going to be decreasing, but how we're decreasing might not look exactly like that. If we have an initial condition greater than 1, yes, we're going to be increasing, but how we're increasing might not look exactly like that. This is what those curves will look like depending on what your initial value is. I hope that makes sense. I'm going to come back in just a moment. We're going to do 3 very quick examples on just getting critical points, showing whether they're stable, semi-stable, unstable, and what their graph should look like. So they'll be very, very quick. I'll be right back. All right, last 3. We're just going to get approximations of what our general solution looks like, and keep that in mind. The pictures we're getting are approximations, so we're getting a general feel for how our general solution will look. The curves themselves will look decidedly different. I'm going quickly through these just to get a picture of whether we're funneling, spouting, or semi-stable. When we talk about solving a differential equation itself and getting the general solution, it will give you the picture of those graphs for real. All right, I'm just giving you a picture of how it could look, just the going away or going to some sort of a critical point. So please keep that in mind. These are approximations of our general solution, but they're valuable. They can allow you to check your work real quick. What they can also do is tell you what should happen in a model of some sort of a population. So it is useful to be able to understand that this gives you a picture of a kind of approximation of a general solution. We're going to do them very quickly. The idea here is let's find critical points. Let's determine whether we're increasing or decreasing on intervals. It's going to give us a look of a general solution or about that. So since this is a first derivative, all we've got to do is set our first derivative equal to 0 to do a first derivative test. Now we're going to be factoring a lot, because by factoring, if our slope is based on a quadratic, which it is here, then a zero product property says that our critical points would be 4 and 1. If we put them in order and we do a first derivative test, let's plug in some values. Now, we can do a couple things about this to make this easier. You can plug in 3 values like 0, 2, and 5. Or you can use multiplicity to show what's going to happen. You see, when you solve a quadratic, what's going to have to happen? So that is a quadratic, right? What's going to have to happen is if you cross a 0, quadratics look like that. 2 of these are going to be positive, and the middle one's going to be negative, or the middle one's going to be positive, and the outsides are going to be negative. They have to alternate, in other words. So we can do that 2 ways, one with multiplicity or one with understanding quadratics. So if you plug in 0 and you say, hey, when I plug in 0, I get a positive, then this has to alternate, and this has to alternate. And you can try this on your own. Plug in 2. Let's see, 9, so plug in 2. 4 minus 10 plus 4 would be negative, decreasing. Plug in 5. 25, that'd be positive, we'd be increasing. You can do that. You can also look at multiplicity. Since this is a factor with a power 1 and a factor with a power 1, multiplicity says that on opposite sides of that 0, that critical point, you will have different signs, which means that here we have different signs, positive and negative. That tells us one side will be increasing, one decreasing. Here you'd have different signs. If that's decreasing, the other side is increasing. You can use some of those things from like a college algebra class to do this very quickly. Sometimes you forget about that stuff, but it is still very useful. Anyhow, this is whether you're going to plug in 3 numbers, use multiplicity, use the fact that's a parabola, which I've just talked about, all 3 parabolas alternate, they're continuous functions, or use multiplicity. We talked about opposite signs for odd-powered, or for multiplicity that's odd. We also talked about just plugging in 3 numbers, 0, 2, and 5, any way you go about it. This interval is going to give us particular solutions, all of which are increasing. This interval is going to give us particular solutions, all of which are decreasing. This interval gives us particular solutions, all of which are increasing. We have a stable and unstable critical point, a funnel and a spout. We've seen it before. Everything would be increasing starting with an initial value less than 1. Between 1 and 4, we'd be decreasing. So typically these things look like this. Sorry, that one won't be there. And then above that, we would be increasing. Now we can see this funnel idea and this spout idea around those particular critical points. That's a very, very loose approximation of what a general solution would be for that differential equation. But it gives us an idea. So it says ultimately, hey, if your initial value is greater than 4, just think about what's going to happen to your population. It's going to explode. What happens if your population is between 1 and 4? It doesn't matter where you are. And after a certain amount of time, you're going to drop to 1. The population is going to have a carrying capacity of 1. If you start below 1, you're going to increase until you get to 1. So you have a limiting population of 1. So that's valuable. How it actually happens, you need to solve the differential equation and model a particular solution based on initial value. But the general gives you a general look and an approximation that says, here's what's going to happen ultimately. The next one. So what happens if I just change the signs? Well, let me ask you that. What happens if you change a parabola to have a negative sign in front of it? Upward opening parabolas, positive in front. Downward opening parabolas with negative in front. So instead of a increase, decrease, increase, we should get a decrease, increase, decrease. The signs will still alternate. It's still a parabola. When we factor this thing, you're still going to have multiplicity 1, which means on opposite sides of that 0, opposite sides of that critical point, you will have different signs. So we are going to have 2 critical points, 2 and 5. Notice how this sign has absolutely nothing to do with these factors, okay? These factors are set equal to 0 themselves by the 0 product property. You don't take this sign and change these values. And what it says for our first derivative test is that if I plug in something like 0, again, we talked about 3 ways to think about it. This is a parabola, so you have to have alternating signs. This would be multiplicity 1 and multiplicity 1, so on opposite sides of your critical point you'd have different values, or just plug in 3 numbers. Plug in something like 0. Now when you do it, do it anywhere. Do it in any of these. I would say probably here's the easiest. 0 plus 0 minus 10, that's a negative. You are going to be having negative slope for every particular solution that has an initial value less than 2. I'm going to say that again, it's very important, very wordy. The slope of every particular solution on this interval, or the slope of every particular solution, depending on whether your initial condition is less than 2, is going to be negative. Every one of those particular solutions will be decreasing. This will alternate, so plug in 3. Let's see, negative 9, 21, and negative 10, positive. Every one of these particular solutions, if your initial value starts between 2 to 5, not at 2 or 5, those are equilibrium solutions. Nothing will change at those values, but every particular solution with an initial value between 2 and 5 will have a positive slope. It will be increasing. And lastly, plug in something like 6. You plug in 6, negative 36, 42, that's going to be negative. So every particular solution with an initial value greater than 5 is going to have a negative slope or be decreasing. This says that that is an unstable critical point. That's a spout. This is a stable critical point. That's a funnel. And what it's going to give us is this approximation of a general solution saying, hey, start below 2. What's going to happen? You're going to decrease. Start between 2 and 5. What's going to happen? You're going to increase. Start above 5, what's going to happen? You're going to decrease. We're going to get this spout for the bottom critical point and a funnel for the top critical point. And again, this can tell you what a population will be doing or a function will be doing. It all depends on where you start. Start below 2, you're going to go extinct. Start between 2 and 5, your population is going to grow until you reach the 5. That's going to be a limiting population. Start above 5, your population is going to decline until you reach the 5. That's a carrying capacity. And so this gives us a model of what is going to happen without having to solve the differential equation. Now, to find the actual curve, something you can really model, you'd have to solve that and get a particular solution depending on your initial value. So I hope it's making sense. I hope that you're with me on, hey, critical points mean something right now. Use some facts of parabolas or multiplicity or just plug in numbers to find out what your general solution would be looking like. Okay, last one. This is kind of similar to the last problem we did before these two, except instead of something minus 2, we have a 2 minus the variable. So let's see what happens with that one without having to do any solving with separable equations here. Well, we would know that if this is our function and it represents a slope, that we have only one critical point. Two. Now that's a cubic. How do cubics look? I really don't care. It's a multiplicity 3. Our slope is cubic. Multiplicity 3 says that on different sides of our different sides of our critical point will have different values. So on one side will be positive and the other side will be negative. They will be different, not the same. So if I take a look at my first derivative test, and I plug in something like 0 to my function, if I plug in 0, I'm going to get a positive, which says that every particular solution with an initial value less than 2 is going to be increasing. Positive slope is increasing. Greater than 2, something like 3. Because of multiplicity, because of the cubic, I'm going to have a different value, a different sign here. So plug in 3, I'm going to get a negative. It says that every particular solution to this differential equation that has an initial value greater than 2 is going to be decreasing, every single one of them. That gives us a stable critical point. That's going to give us a funnel. And what that looks like for us that's kind of neat, is that at x equals 2, at x equals 2, come on, Leonard, at x equals 2, we have an equilibrium solution. If we start an initial value at 2, that population, whatever this is, this function will not change. If we start below that, it will increase until we reach 2. If we start above that, it will decrease until we reach 2. That's it. That's as much as we need to go on this one. So I hope that I've made it very clear on the interplay between a first derivative and a first order differential equation, that they're representing the same thing. But going backwards from a differential equation, you're not quite sure exactly what your original function looks like. And so we get a general solution, and it's dependent on what our initial value is, very dependent on that. We can get an approximation by just doing a first derivative test. But to get the real picture, we'd have to go ahead and solve our differential equation, and we'd have to know an initial value, because that's going to dictate what our graph is actually doing. Also, I hope that I've kind of refreshed your memory on how to deal with some of your sign analysis, understanding multiplicity and the shape of your graphs. So I hope it's made sense. I know it's a long video. I hope that you were with me the whole time. Next time, what we'll talk about is we'll take a look at some different examples as far as harvesting and stalking is concerned, and how that affects what's going on. We'll talk about bifurcation point, what that even means. For right now, if you've understood how to get these graphs from your differential equation, you're doing great. So I'll see you for another video. Hope you're doing well. I'll see you soon.